Good afternoon, everyone. Thank you for attending this week's Brown Bag Launch Seminar, and we have two presentations today. The first presentation is from Nicolas. He is a fourth-year undergraduate student and about to graduate this semester. He has been working with Dr. Kyriakos Vanvadakis since for 2020, and today he will present sensitivity and robustness in the control and planning of UAVs with temporal logic objectives.
Okay, great. Thank you. Cool. So, hello, I'm Nicolas and Miguel. And yeah, as Dr. Sun said, I'm presenting sensitivity and robustness in the control and planning of UAVs with temporal logic objectives. So starting with the outline of sort of this whole journey, we're going to start by motivating urban air mobility and see how that necessitates some research. We're going to look at signal temporal logic, look at the reason for using that and what it is and how you notate it. We're going to look at trajectory planning briefly to introduce an example mission that shows the planning and execution of a trajectory with these objectives, and it sort of combines everything we talk about. And then afterwards, we're going to look at the errors in that mission to measure the sensitivity and robustness and get a feel for quantifying that. So that's sort of the outline for the whole plan. We'll start with this idea of urban air mobility, which I'm sure is not unfamiliar to most of the people here today. It's a transportation system in an urban environment. It can be used for package delivery. It can be commercial taxiing, personal vehicles. The idea is basically just to have flying vehicles in a dense urban environment. And here are a couple examples. NASA and the FAA both have been doing research. It's a common topic in industry and in academia. It's been growing in the past few years. And what's important from this is we can make things fly, and that's not too difficult at this point. But in order for things to fly in a city where it's very close to people, it's going to have to be very safe, very reliable, and very effective, very efficient. So these are things that we have to keep in mind while we approach this problem and develop these systems. So what I'm looking at today is using signal temporal logic to write out these complex requirements that these urban air mobilities have, and analyze them in a meaningful way. So without further ado, we're going to talk about temporal logic. So logic brings back ideas of AND gates and OR gates from circuits, which is sort of like that, but a bit more developed. Temporal logic incorporates time elements too, so it's not just a signal going from AND and OR. There are also temporal constraints on that, and there are multiple kinds of temporal logic, different languages. There's linear temporal logic, signal temporal logic, among others. So we're just looking at signal temporal logic. The reason for this is if you look at this figure on the top, it has an urban area. It's taken from a different paper, but it shows there's a lot going on. There's areas you can't fly into, that if you have multiple drones, they'll have to avoid colliding. You have to manage the airspace depending on the mission. There's going to be different missions going on at the same time. And all of these break down into spatial, temporal, and reactive requirements. So ultimately, you'd like to solve all these requirements together. You won't be picking and choosing based on different systems. Unfortunately, English is not a very clear language. So we want to find a way to take English, a requirement written out in English, and convert it to a formula that is clear and executable, very concise. Ultimately, we want it to be succinct and unambiguous. And that's what signal temporal logic can do for us. It can take these vague words and convert them into a formula. So it's very useful. And then on the bottom right, we have a figure. It's sort of just identifying airspaces is what the idea of a simulation would look like. You denote airspaces by different areas and stuff like that. Touching back on why signal temporal logic specifically, different temporal logic languages have different pros and cons. And one of the pros of signal temporal logic is it can scale to multiple vehicles well. So when we start adding multiple drone missions, that is not really a problem from the logic side. And then it also has explicit time bounds, which is helpful for the example we'll show later on. Also, the main reason is STL is very effective for the real-time behavior of hybrid systems, where hybrid systems, they combine time-driven systems and discrete event systems. So signal temporal logic is sort of used pretty frequently with this, and we'll see more of what it is exactly right here. Getting into the notation of it, we have the usual suspects, the and, or, and negation operators, but we also have these until, eventually, always. These are more time-related operators. So you can see how they all start to come together with these examples over here. And also a specification is it's also known as a formula, this phi. And we have a state and a robustness value. The robustness value it'll come into play later on in this presentation. So I have two examples here. The first one, this is just for a random vehicle. It doesn't have to be urban air mobility. It can just be anything. But a vehicle speed, I have it in English and translated into STL. The vehicle speed has to be less than a maximum, and the RPM has to be less than a maximum. Pretty straightforward. The way this works in STL is we have the always operator. And while always, the speed is less than a Vmax and the RPM is less than Vmax. Very straightforward. And it's written out very straightforward as well. With this second example, it's a little less straightforward. The requirement is this vehicle speed cannot reach V0 in tau seconds with RPM always below n critical. With this example, you sort of start to see how English can be ambiguous because it's saying, you don't know, can it reach V0 after tau seconds with that RPM? Does the RPM have to be above n critical in tau seconds? It can be interpreted different ways, and depending on how you write it out, it can be very ambiguous, and you might not even notice that. So when we write that in STL, we have this first term, eventually between 0 and tau seconds, with a speed greater than V0, and then the negation operator. So that speed is never greater than V0. And always the RPM is less than n critical. So yeah, that just expresses it. A note, these are not unique. You can also change these expressions to maybe remove the negation operator and change the sign. They're not unique to each requirement, but they are a useful way to put it out in a way that is relatively easy to program into a computer. So the next step is, with this whole idea of STL in mind, we're going to look at an example, and we need a little bridge to get between the language and the actual example. So where does it factor in? Well, before all these vehicles take off, they have a plan of where they're going to go. If you have a bunch of, say, delivery vehicles, before they take off, they have a plan of where they're going to go. That plan is calculated using the kinematic constraints, the maximum speeds, all of that of the vehicle. That's not new, but the STL formula is considered when you're calculating that. So while you're solving that optimization problem, you want to find a path that is dynamically feasible, but also does not violate the STL formula that you made. So you can solve them together, you can solve them one after another. The idea is they're solved before the vehicle takes off. And it's usually online, computed with, these optimization softwares, Casati, for example. And then those are uploaded to the vehicles, which can be online or offline. And then the vehicle controllers, they have a controller that regulates, air, tracks the path as best possible, and affects the control surfaces, motors, stuff like that. So what we're going to do is we're going to do a little simulation of this whole thing with an example mission. So this example mission I came up with to sort of introduce these ideas and visualize them in a relatively easy way. This is just a single drone delivery mission. So the drone is going to fly to a place, deliver a package, fly to another place. And we have these airspaces, quote unquote, that are predetermined. These are just three views of the same thing. The red airspaces are bad, and we're going to try and stay away from those. We're going to first go to this blue airspace and then to the green one. The blue one we're going to try to get to at most 5 seconds, and then we're going to get to the green one after at least 15 seconds from the start, from this origin point. So there are spatial and temporal requirements that are specified here. How are we going to write this in a STL formula? Well, it's pretty straightforward. We have eventually, within 0 and 5, the position will be within the blue airspace. And eventually, between 15 and 20, the position is within the green airspace. Reaching the blue airspace within at least at most 5 seconds, that's sort of indicative of you have to deliver a package in at least this and at most this amount of time. Landing after 15 seconds, that's more indicative of like a speed limit constraint that may be applied to it. So it's going to go slower going from blue to green. And then also we have we're going to do the spatial constraint. This first line, this top part is the temporal, bottom line is the spatial constraints. We have always the position will not be in unsafe area 1 and the position will not be in unsafe area 2. So pretty straightforward, nothing too complicated. This goes into, so when a trajectory is computed, it has to satisfy this mission statement. There are very varying levels of complexity, but on a very basic level, it can be set up in MATLAB in the form of if statements, else statements, while loops, to put these spatial, temporal, etc. requirements in. So you just check the trajectory when you plot it using whatever. Trajectory generation is like a whole field of its own. So it's just plotted and then make sure it satisfies these conditions. Next slide, we have exactly that. There's a dotted line. It might be hard to see through the computer. That is the planned trajectory for the vehicle. So this is calculated and then it's verified that it meets the STL constraints. And I'll run it. So we see this little triangle come up, flies over the first red one, lands in the blue, and then as it goes from the blue to the green, it goes a bit slower. All the while, it's avoiding the red airspaces. So it meets the temporal and the spatial requirements for the mission. So all's good on that end. But what's interesting is how we develop after that, because there's more to be said. So this is just plotting the planned trajectory. It's not the actual trajectory of the aircraft. The actual trajectory varies because of the kinematics of the aircraft, noise in the system. It's going to be oscillating about, hopefully close to, but about that planned trajectory. So that moves into the idea of controller. So there's a controller on the vehicle, and it's going to be measuring the error between its position and the planned trajectory. And ideally, you want to penalize that. So if you notice the vehicle is getting further away from the planned trajectory, that's going to be heavily penalized. You get closer. That's pretty straightforward. Also, a second issue that comes up is, for example, this planned trajectory satisfies all the conditions, but it gets pretty close to this red airspace, like at this corner right here. So if a vehicle is flying with some sort of noise and oscillates about the planned trajectory, it may, go over that line and infringe on the red airspace, which is not good. So there's a safety margin that's applied, and this is bounded by the worst case scenario. This is where that robustness value that came in when we were talking about the STL notation. Part of that STL notation would be, for the mission, would include having a robustness value that's less than, say, the worst case scenario, whatever your that's like defined as your safety margin. So you've got to not only satisfy the requirements, but also include a safety margin there. This is a general error state dynamics equation. It takes the error state of a present position and also calculates based on the acceleration and the inertial properties of the vehicle, or to see how the error state changes over time. So that's going to be used. Now, I'm going to do a quick aside. We're going to use this idea of error state dynamics in a second, but I'm going to do a quick aside to tell you what I mean by accuracy and robustness. Because those are two buzzwords, more or less, and they're used differently all over the place. This is how I want to use them here. So a bit aside, Models are inherently imperfect. That's why, there's errors always. We're going to look at a general perception-based system. So just hold all that like urban air mobility example stuff to the side for one slide. We have a general perception-based system here. It has on the top a state estimator, or a state estimation formula, and on the bottom is the input and the output. So this A matrix is in the top, and that combined with like a linear filter K forms a state estimator, which is used to estimate the next state of a system. This could be like a car, a plane, a vehicle, any sort of vehicle. And then in the bottom, an input with the C matrix plus some noise gives the output. Pretty straightforward. If we wanted to analyze this, we would combine them and find the error. So the error between the estimated state and the outputted state. That would be of interest. So doing so, you have a P matrix, which is shown here. And this is glossing over a lot of math, but this is just the results of that. This P matrix is the estimation error. And you start by looking at the stability of that matrix for an input K. This is a linear filter gain. You can see that the trace of that matrix so we're going to define as the filter performance. So you can change K such that it minimizes this metric, and this corresponds with the accuracy of it, the accuracy of a system for a given like linear filter. So you have all these dials you're changing, the linear filter, the matrices, and these are like the metrics you're trying to achieve. Going a little bit further, we can take the derivative of that with respect to R. R is like a measure of the noise. So take the derivative for changes in noise, you get a sensitivity metric, right? So you'd also like low values of sensitivity. You don't want a small change to make it like the system have a big change. This corresponds with the robustness of a system. And you combine these ideas into an optimization problem, solve for a sensitivity such that the filter performance meets a certain criteria. But unfortunately, it's a trade-off. You can't have the best of both worlds. For example, if you have, say, a low filter performance, which is desirable, they tend to on the order 10 to the 1. That's the script P. When you have script P here, that's on the order of 10 to the 1. If the noise is also on that same order, when you take the derivative, that derivative step on the order of 10 to the 1, it's going to end up being a very large value. For any change here in the derivative, it's going to result in a huge change in the filter performance. So the sensitivity is going to be huge, right? So you can see intuitively there's sort of trade-off. There's more investigation there, but this is just an overview. So when I say accuracy and robustness, this is sort of what is implied. Going back to that example, stepping out of the aside, we'd like to look at that vehicle tracking the path. So when we put it together, the example, the little video I showed only has the planned path, but not the actual path. I couldn't get it to work exactly by this time, but we're still in the middle of the semester, so I'm working on that. The idea would be to visualize that error in a meaningful way. So I've included charts here. Quantitatively, they're not important. Qualitatively, they are useful. They show a planned and a tracked trajectory and a robustness bound. So when we're designing urban air mobility vehicles, we'd like to have as low a robustness bound as possible while still being safe. But there's a trade-off. When you decrease the robustness, you sacrifice some of the accuracy. Or you decrease the size of the robustness, you're sacrificing accuracy. And this can become another optimization problem to have. And ultimately, this would contribute to providing safe, reliable ways to get vehicles around in a densely populated area. That's sort of the ultimate goal. It's not for a specific project, but in general, how do you plan and control these vehicles in a meaningful way? So with that, these are my references, and thank you all for listening.
Thank you very much. Are there any questions from the audience? You can raise your hand or you can use the chat function. To start with, and my son, who is 8 years old, is also listening to your presentation, and he likes your talk very much, and he has a question he wants to ask. Okay.
Okay. Oh, what's that?
What is a geofence?
Oh, a geofence. Yeah, so that's a good question. A geofence is sort of an area that's blocked off. So you can't see it outside. If you go outside, you wouldn't be able to see it, but those like GPS coordinates are blocked off and they make like a little fence of GPS coordinates. So like if your phone can do it. If you like walk in a certain area, it'll like alert you. Yeah.
Thank you.
Of course. Thank you.
Any other questions from the audience? Seems like no. Okay, thank you very much, Nicolas.
Okay, thank you.
Yeah. So let's switch over to Austin. Next, we have Austin Hatch to give us a presentation, and he is a fourth-year aerospace major in our BSMS program, and this is his third semester as an undergraduate researcher on the hypersonic vehicle Grand Challenge project, where he has been focusing on the propulsion modeling. In the fall, he will be starting his master's degrees as a graduate research assistant in the ASTL.
Awesome. Thank you so much, Dr. Sun. And sorry for the technical issues. I appreciate everyone's patience with that. So today I'll be talking about my work on creation and exploration of an MDAO environment for a hypersonic vehicle. This is part of a grand challenge project within the ASDL, and this is my third semester on this research project. Next slide, please. Just a brief outline of what I'm going to be discussing today. I'm going to talk about hypersonic flight, what that means, along with why it's relevant for us to study this, along with the challenges and opportunities related to hypersonic flight. I'm going to discuss what this Grand Challenge project is about, what the purpose is, what our research objectives are, and I'm going to talk about what an MDAO environment is, along with how we're modeling the geometry, propulsion, trajectory, and thermal protection of our hypersonic vehicle. Next slide, please. So as a general rule of thumb, hypersonic flight is defined as just any Mach number greater than 5, although this is not really a hard limit, as really a better way to define it is when physical phenomena such as aerodynamic heating become significantly more important than that of just supersonic regime. So this could happen at Mach 3, it could happen at Mach 7. So Mach 5 is just a general rule of thumb and not kind of a hard transition. And what I mean by certain physical phenomena become significantly more important is that even the chemical and thermal properties of the air itself around the vehicle is altered due to the shock compression and viscous dissipation at such a magnitude that it becomes one of the major drivers in the design of a hypersonic vehicle. Next slide, please. So in recent years, U.S. funding for hypersonic research has increased significantly. The Pentagon just this last year has requested $3.2 billion in funding for hypersonic research alone. So that's quite significant. And this has been increasing from past years' budget requests as well. And one of the main reasons the Department of Defense is so interested in hypersonic research is because Russia and China has increased their interest in hypersonic weapon systems throughout the recent years as well. So as you can see on the figure on the right, a hypersonic vehicle, whether that be a missile or some kind of surveillance vehicle, it has a much shorter range for detection than something like a ballistic missile would. Additionally, having a hypersonic vehicle, it's able to be much more maneuverable than something like a ballistic missile would be, and so it's better at evading potential ground defenses from the target. Next slide, please. And the application for hypersonic flight is not just limited to defense, but it also includes applications for commercial flight. And so this would basically make flights to anywhere between any two places on the Earth less than 2 hours. So a New York to London flight could be as short as 90 minutes. So that could be a major step in commercial travel, as well as it can provide a more efficient launch to orbit than traditional rockets have provided in the past. A hypersonic air-breathing vehicle could have a single-stage launch to orbit, or it could be the first stage of a multi-stage launch. Next slide, please. So some of the main challenges with hypersonic flight are, as I said before, the intense aerodynamic heating. This can be so intense that it can reach temperatures as hot as the surface of the sun, which is quite astounding. Additionally, the air molecules can dissociate or ionize around the vehicle as well. Another issue is that there's no single air-breathing propulsion system that can accelerate a vehicle from complete rest to hypersonic speeds. An engine such as a scramjet cannot operate at rest, so you would need something else like a turbojet or a rocket booster in order to accelerate you to the hypersonic speeds at which it could operate. Additionally, there's a lot of difficulty replicating hypersonic flight with wind tunnel testing, and there hasn't been that many actual flight tests of hypersonic vehicles compared with subsonic vehicles, for instance. So there's less testing that's been done so far. So plasma surrounding a vehicle from the intense aerodynamic heating can inhibit communication signals with the vehicle, which can become an issue with navigation and other communication. Maneuvering is also quite a difficult task at these speeds due to the high structural and dynamic loads that are going to be on the vehicle just due to the nature of the high speeds. And another major factor is many of the physics and constraints are highly interdependent with the vehicle, and we'll talk about that more later. Next slide, please. So a little bit about this Grand Challenge project. It's a graduate student-led project, and some of the issues we're trying to address with this project are that much of the data and tools for hypersonic research is classified. In addition, the design of hypersonic vehicles is highly interdisciplinary. And so in order to address these issues, this Grand Challenge project seeks to build on previous work done in creating and exploring an MDAO environment for hypersonic vehicle. And MDAO just means multidisciplinary design, analysis, and optimization. So it's concerned with solving design problems involving coupled numerical models of complex engineering systems. So for a hypersonic vehicle, many of the different systems are very interrelated. So maybe a more traditional approach to design isn't going to be as effective as approaching it with a MDAO mindset. Next slide, please. So specifically, each year, this Grand Challenge project has a slightly different objective or design in mind. So this year, it's the design space exploration of a refurbishable hypersonic vehicle, specifically for use in intelligence, surveillance, and reconnaissance, which is abbreviated ISR. And there are three core areas of exploration where we would like to examine the trade-offs. And these are between propulsion, vehicle geometry, and trajectory. And part of this mission profile, it can be launched from either air or sea, and it will be recovered at sea and should be refurbishable within a time scale of days. Next slide. So this is a brief graphic of what the general mission profile is. So we're going to have a launch point, as I said, from sea or air with a time and a distance dash to our our area where we want to perform reconnaissance, and then we have an area where we're going to be performing that reconnaissance and performing loiter maneuvers, and that has a distance that we might want to maximize in order to surveillance the biggest area. And then we have a distance to recovery and splash down into the sea to be recovered and refurbished. Next slide. So this is an n-squared diagram of our MDAO environment. And as you can see, it's highly interdependent between each systems. So the geometry has a major effect on aerothermal properties, propulsion, weight and volume, thermal protection sizing. And this tends to be the nature of hypersonic vehicle design, as all the aspects are very interdependent. And we'll see that as we discuss each one more in depth. Next slide. And so this was our initial morphological matrix of all the different configurations we wanted to examine for this mission. So as you can see, we have 9 different options for the vehicle geometry. 2 different launch options, sea and air, as I mentioned before. A few different propulsion options, so rocket only or scramjet only, or some kind of combined cycle with a rocket booster and a scramjet. Several different vehicle types, so a glider to where it has no propulsion system, air-breathing accelerator where you would have thrust constantly greater than drag, so you would be accelerating throughout the whole flight. An air-breathing cruiser to where thrust is equal to drag, or a boost glide where you would boost up to some high altitude and then kind of glide down on a skipping trajectory, which can make it difficult for an enemy or target to predict where the aircraft is going. And then a few different fuel types, as well as multiple options for thermal protection, be that ablative or non-ablative, and having a cooling system potentially if it's non-ablative. Next slide. So initially, this gives us 729 total configurations in this preliminary concept, which is just infeasible due to our time and resource constraints. So we have to down select to fewer combinations we want to model. And part of that includes identifying just infeasible combinations. So for example, if we have a glider aircraft, we're not going to put a scramjet engine on it just by definition of having a glider aircraft. Next slide. So for our vehicle geometry, we will be trying to model all 9 combinations, time permitting, using a program called CB-Aero, which calculates the aerothermal properties of the vehicle based on its geometry, using panel methods and whatnot. And some of the main considerations for the vehicle geometry are the fuel capacity. So how much volume you have is going to enable you to have more fuel. The engine size, so because the propulsion system is highly interdependent with the geometry, that's going to affect the size of your engine that you can put on the vehicle. Lift to drag ratio, thrust to drag ratio, and then the temperature requirements as well, because the geometry can highly affect the hot temperatures around the vehicle. Next slide. So as you can see, one of the major trade-offs for vehicle geometry is lift to drag ratio and volume. So as you can see, they're inversely related. So if we are trying to model a glider, for instance, we'd probably want to choose bodies that are in that upper left quadrant, because you're going to have a high L over D, and you don't need a lot of volume because you're not trying to carry fuel. Whereas if we want an air-breathing accelerator, we'd want to choose a vehicle geometry that's in the lower right, as it would provide the most volume so we could have the most fuel. For an air-breathing cruiser, you could probably choose something in between that offers a good balance between both of those constraints. Next slide. As for the propulsion system, we have a Python code that we made constructed to model a scramjet engine, and this has inputs of different Mach numbers, altitudes, angles of attack, and throttles. and this takes inputs from vehicle geometry, and you can see this in the figure below. It's kind of a low fidelity model of a scramjet engine. So the vehicle forebody, which is determined by the geometry, creates a shock which helps compress the air for the scramjet engine. So depending on the shape of the geometry and the different lengths, that's going to change the operation of the propulsion system. And then additionally, we have a Python code made to calculate just solid rocket booster mass required to reach a certain Mach number in altitude, because, as I mentioned before, you can't operate a scramjet from rest. So we need to first accelerate the vehicle to hypersonic speeds where the scramjet can work. So we're just using a solid rocket booster, and we're just modeling that by calculating the mass of the booster required using an energy method. So next slide, please. So as I mentioned, it's a pretty low fidelity model, and some of our assumptions include 1D flow, frictionless flow, no ionization or dissociation, and so this provides a low fidelity model. But one of the benefits of this is it allows much shorter run times as opposed to CFD, for instance. And additionally, CFD has a very specific application in mind, whereas we're trying to model a more general idea of the scramjet engine in order to explore the trade-offs. So CFD wouldn't be necessarily our best option. And so what this code calculates are the pressures, temperatures, Mach numbers, flow values basically throughout the engine, and it calculates the thrust and fuel consumption of the engine. And I just put some figures in of kind of what the engine map looks like for Mach number and static pressure. Next slide. So another thing we've thought about adding and we would like to add in the future is the ability to model combined engine cycles. So you could have dual mode ramjet, scramjet engine, or add the ability to model turbojet engine into our existing model, which would expand our design space. So we could explore more trade-offs within those different propulsion systems. Also, as I mentioned before, we're going to explore the different fuel types. As you can see, one of the main trade-offs between different fuel types is the mass energy density and the volumetric energy density. So that's a trade-off we're going to be exploring soon. Next slide, please. So for trajectory, some of our main alternatives are these three, which is the boost glide. So as I mentioned, you boost up to some high altitude and kind of glide down on a skipping trajectory. Cruise, air breathing cruise. So that's where the scramjet engine would be operating, thrust equal to drag. And then unsteady acceleration. So the thrust would be greater than the drag. And these all have a common that they all require an external propulsion system to first bring them into the hypersonic operating range. So that's where the solid rocket booster mass comes into play. Some of the main considerations for trajectory are the time over target, right? So the purpose of this vehicle is to perform surveillance over some target area. So we want to consider how much time we can have over target, how much range we could cover over the target. Additionally, trajectory takes into account the aerothermal constraints. So how fast the vehicle may accelerate is going to be limited to the material's ability to withstand high temperatures. And the trajectory is very highly dependent upon both the geometry and propulsion modules as well. So next slide. As for thermal protection modeling, we have two main design alternatives: ablative, meaning the material gets worn down over the course of a flight, versus non-ablative. And an option we're also considering for the non-ablative material is some kind of cooling system. So this could be using fuel to help cool the surface of the vehicle. And this thermal protection sizing is determined using a tool called TPS Sizer. And another consideration for thermal protection is that the vehicle geometry can be altered in order to change these aerothermal conditions around the vehicle, which comes into play when considering the thermal protection needed for the vehicle. Next slide, please. So as for the scope of our modeling, due to time and resource limitations, we had to decide some factors that we just couldn't model in our analysis. And so these include modeling the different sensors that we would have on the vehicle and the payload. Additionally, we're not considering the launch recovery or refurbishment support systems of the vehicle or the communications and navigation functionality. We're kind of just assuming that the vehicle is able to communicate and navigate, and we're not trying to model that specifically. Another thing we're not covering is the structural and material considerations that we'd have to take into account for the vehicle landing in the water for recovery. And then we're not looking into detectability of the vehicle geometry, just because the heat signature itself is already going to be detectable. And just the nature of it being a hypersonic vehicle, its speed and altitude are going to provide security from any external threats. Next slide. So this is a concept of operations for our vehicle. So we have a launch option from either air or sea, where we will climb, dash to the target area, perform surveillance and loiter maneuvers, and then return, descend, and splash down in the water to be recovered and refurbished. And the altitude, time, speed, rate of climb, range, all of these are going to be design parameters to be explored within our modeling and simulation. So if we want to maximize our range in the target area, how does that affect our other parameters? Next slide, please. So the work to be done soon in the near future is to actually then explore this design space. So we've already gotten the different modules to work. So now we're able to start running some of these different configurations and explore these trade-offs. And so the major questions we're looking into are, what are the major trade-offs between these design priorities, as well as what is the applicability of a certain vehicle designed to alternate mission profiles. So if we changed the mission profile, would this vehicle configuration be able to perform that mission? So soon we're going to be exploring this design space, varying geometry, propulsion system, and trajectory. And in doing so, we'll get to see the major trade-offs, and we'll get to see sensitivity of each of these different tools or assumptions, how that affects the vehicle design. And that will give us insight into what tools maybe we need to increase the fidelity on, because this is very much a first principles project, but exploring these trade-offs and these sensitivity studies helps us see what areas we would want to improve upon in the future. So that being said, next slide. I'm open for questions.
Okay, thank you very much. Are there any questions from the audience? Okay, I have a quick question. And did you consider a noisy generation in your design?
A noise generation, is that what you said?
Yes, that's what I said.
No, that is not something we've considered. Just due to the time and resource constraints, we very much have had to limit all the different design parameters we've been looking at. So no.
Okay, thank you very much. Any
Thank you so
questions
much.
from the audience? Okay, seems like no. Thank you very much, Austin.
Thank you so much.
Take care, everybody. See you next week.